doing?
Good to see you, sir.
Same here. So we're now here with Dave Navant, who is the interim chair of electrical and computer engineering. He's got several stops lined up for you today. So I'm going to turn it over to Dave, and then at the end, you're going to turn it back over to me.
Perfect. Thank you, Dana.
Okay.
Welcome,
Take
everyone.
It away.
Great to have you all here with us virtually. So as the name implies, we have two programs in this department, electrical and computer engineering, two separate degrees. Although there's a lot of overlap in those degrees, and so some students will actually complete both, take a dual major, which of course makes them very competitive on the job market. Each of our graduates has typically about 2.8 jobs available to them in Maine, so lots of opportunities for our students. And that of course means they can demand very high salaries. So some of the starting salaries are amongst the highest of any four-year degree graduates. So that's important. It's also important that they're working in fields that are impacting society. And what we're going to do in this tour is highlight some of those. So if you'd like to follow me upstairs, we'll make our first stop, which is on high altitude balloon. Here we have Professor Rick Eason and his student Joseph Cutton, and they have a program where they send balloons up to extremely high altitudes with all kinds of very interesting payloads. So, Rick, I'll turn it over to you and Joseph.
Howdy. So we have a high altitude ballooning program here, and at the University of Maine, we've had this since about 2011. And with this, we send up, essentially it's weather balloons, call it scientific ballooning, whatever. And we just had a launch last week. We launched a few payloads for high schools and things. And what we have here is just kind of like a little demo of what goes on the balloon. It's Joseph Patton, one of my students here. I'll let him kind of walk you through a little bit about what's on the string.
Hi there. So this is our kind of payload. This is what we would end up sending up to about 120,000 feet. So at the top here, this is actually a nozzle that connects to our large weather balloon, and you put in the hydrogen here to fill up the balloon, and we actually 3D print these in-house ourselves. Here we have our parachute, so when the balloon pops up at 120,000 feet, this parachute will open up and our payloads will gently come down to Earth. Over here we have some of our telemetry payloads. So this payload will send GPS coordinates to us to help us find the balloon and also chart its progress. And we also take video of the flights using GoPros that you can see here. And as a backup, if our GPS doesn't work, we have this device called the Beeline, and we can use directional antenna to help us find our payloads in the woods after the balloon pops. Here, as you can see, we have some student payloads. So this payload was designed by a student who took our high altitude ballooning course, and he put together this circuit that actually communicates with GPS satellites and gets us our GPS location, and he programmed this board himself. Over here we have this very cool payload that employs these fins to help guide the balloon as it ascends. It tends to turn and spin, so these use motors to kind of help the balloon stay steady to help point a camera. And as you can see here, these are what our payloads look like when they're strung together. We use flight grade string that has a specific breaking point so that if an aircraft hits the payloads, it'll break at just the right pressure. Yeah, so this is generally what one of our payloads will look like. We can send up as many boxes as we want, but we try to keep it under 12 pounds. And each of our boxes, I believe, needs to weigh under 2 pounds. 4 pounds. Yep. So, yeah.
How about the CubeSat one?
Oh, so also we are collaborating with a CubeSat program that I'm actually the project manager of within one of the other labs on campus. And so just last week we sent up a payload for this high school that is one of our sort of science teams for that project. And we tested one of their payloads just last week using this high-altitude balloon program.
So Joseph, what are the scientific implications of this work? Why is this important that you do this?
One cool thing about these high-altitude balloons is that they say the atmospheric conditions up there are similar to the surface of Mars. So instead of spending millions and millions of dollars sending your payloads to Mars, you can test them up at high altitudes.
And that's the same with the CubeSat program. With the CubeSat program, the students are building payloads that will eventually go and be launched and orbit the Earth. And so it costs tens to hundreds of thousands of dollars to send up a small payload and have it orbit the Earth. So you want to make sure it's working really good. So we send it up on a high altitude balloon to test it out, go through the paces, make sure everything's working good before you spend the big bucks and send it on up.
And those heights were about 120,000 feet, you said?
Yeah, we get up to 120,000. We've been up to 126 or so, but typically they're somewhere 110, 120 for our launches. Yeah. Another thing I can tell you about is we did a national. There's a national eclipse ballooning project in 2017 for the eclipse. And I have a few things down here. I hope they show up on the video, okay? But on the screen here, what they did is they had a website. There were 55 ballooning teams across the country. And what we did is we had a tracking, we had cameras on the balloon and a tracking station, like this tracking station that we had. And we actually had two of them, two complete setups. And I took about 20 students down to, almost 20, 18 or so, down to South Carolina. And we launched 2 balloons during that total eclipse. So just a few quick pictures here to kind of run through. We're setting up, getting our 2 balloons ready. And anyway, they're pretty big weather balloons. And you see the payload string there. We were actually lucky enough that one of the students just happened to catch the balloon eclipsing the sun on one of the 2 that went up. And that's just, some students aren't there, but that's a large number of them. Whoops. And we have just a big crowd there at Clemson where we were launching from. And you can see the shadow of the eclipse on the Earth. And that's kind of the goal of the project. We were live streaming this view across the country. And you can go to that first web page that I showed you and click on an image and see what the view looked like from that balloon at that time. And so we had a pretty successful run there. One of those worked pretty good throughout the flight. You can kind of see what it looks like. When we're up there 120,000 feet, the sky's just black. You can see a little blue line of space there. And balloons come down, pop, and we end up somewhere in the, there's a, real quick there, that's a slow motion balloon burst. Had a camera pointing straight up at it. You can kind of see what it looks like as it's a slow motion burst. But there's another eclipse coming up in 2024. It'll be going right through Maine, and for this version of for this eclipse, Montana State was managing this, and they've actually roped me in to help manage a portion of that. I'll have if the grant goes through, I'll be looking for students to hire throughout their whole career here, their undergraduate time, to help us with the program. So I'm looking for some students to help. Pay them too. What's better than that?
It's incredibly exciting.
Yeah.
So Joseph, do you want to tell us a bit about why you're here at UMaine and what your plans are?
Yeah, so I'm a senior at the University of Maine. I've actually been working on this project, this program, since I was a freshman. I got hired in my second semester, and I've been helping with launches and programming payloads and all sorts of things. And I'm actually sticking around for some grad school. I'm working for Dr. Eason probably in grad school, and I'm also going to end up working for another one of our professors, Dr. Betty, in the Wireless Sensing Networks Lab. So we have a great program here. It's very rigorous, and there's lots of opportunities for research, and you can really go above and beyond just your coursework if you're interested and motivated. There's plenty of stuff to do here.
Excellent. Well, thank you, Rick and Joseph. We're going to move on now.
Yeah.
Thank you for your time. All right, so we're going to head on to the undergraduate microwave lab. Professor Mauricio da Cunha. Hey there, Mauricio.
Hi. Welcome. I'm ready to talk.
Go for it.
So this is the undergrad microwave engineering and sensor lab, right? And the major activity here is actually two courses, EC 453, which is microwave engineering, and 466, which is sensor lab. One might ask, what's the importance, right, of this topic? The importance is essentially all our consumer electronics, cellular phone, high-speed communication, right? These days are use this thing, and sensor by themselves are very self-evident, right? We use that in all the cellular phone that you're using there, and advanced manufacturing, healthcare, environmental monitoring. So this lab in particular is very hands-on, right? The students come here and have a capability of actually building, designing, fabricating, building the device together with the theory. So it's a multidisciplinary lab as far as sensor is concerned. For instance, the students from other disciplines can come here and take this lab. And the truth is, it's a very high demand professional radio frequency engineers that have expertise in microwave. So the reason is, if it's a cool job, right? Cool fun stuff, pays well, and you have job when you graduate, why not come here, right? As I said, it's a hands-on job. I have here some samples of device that the students during the course, right, have designed, fabricated, and tested. We actually fabricate these devices using this milling machine here, right? So one of these devices that was just fabricated here is being tested by shear laser, right? We see there how the milling machine works, and we test essentially this type of device here, right? That you have here. It's a band pass filter. And as I said, as far as sensor is concerned, right? You can see also Shirleka is a student here. She can talk a little bit about her work and what she's testing now.
Yeah, I'm Srilekha. I'm an international student at UMaine in the Department of Electrical and Computer Engineering. I'm here because I was always kind of fascinated about wireless communications and how it actually works. So that's what pushed me towards ECE. So here I fabricated a bandpass filter working at frequency of 2.4 gigahertz using the milling machine and Broadmaster software. And now I'm testing the same using a vector network analyzer.
Yeah, one can mention that all this equipment, right, is industry standard equipment. So essentially what the students use and learn here, they're going to use in their jobs, right? And as I said, there's a very high demand for that type of training here. Joel is another grad here. He's doing work on biomedical, so it's a example of multidisciplinary effort. And as far as this sensor course that I mentioned, right, Jonathan was a student here. They implemented this here in his group, right? That device there. I'll let Jonathan talk about it.
I'm Jonathan Kincaid, graduate here spring of this year, 2020, now working at UMaine Frontier Institute for Research and Sensor Technology. One of our courses of undergrad, the Sensor Technologies and Instrumentation course, a team of us built this circuit. Humidity control plant watering circuit. The inner orange reservoir represents either a potted plant or residential lawn or even a field of crops. So in classes like this, you're very hands-on, build something that works in the real world, and this idea, while small, can be scaled up to any degree. And it's just a way to show that sensors work in the real world and gives kids an exciting thing to put their hands on to demonstrate these concepts.
I think one thing we can point out too is that we're incredibly well instrumented. So as Mauricio said, if you look at the instrumentation we have just in this lab alone, it meets industry standards. So as you said, the students are getting training on equipment they're then going to be using out in the field. They're not going to be playing catch up when they get out into industry.
And what's important to add to what David's saying is that the students have the opportunity to actually work with and touch this equipment, right? Lots of very big universities do not offer that capability, and we do offer that capability that the undergrads can come here, have access to this expensive and dedicated equipment, and the groups are relatively small, so they have easy access to colleagues, myself, another professor, so that's a very big advantage for this training.
Yeah. And the last point I would make in this area is that all of our classes are taught by PhD faculty. Okay, we don't have classes being taught by graduate students. They may assist in grading perhaps or filling in, but all the courses are taught by faculty, and that's a very important distinction from other programs.
Sure.
Okay, well thank you all. We'll move
you.
on. Appreciate your time. Okay, so next up the list we have Professor Yuri Aminatoglu. He's going to be talking to us about the electrical engineering program and some of the relevant labs.
Yes. Hi, I'm Nuri Amanatoglu. I'm an associate professor here in electrical and computer engineering. I'm going to talk about the circuit sequence, which is the core of our electrical engineering program. Why circuits? Because they're everywhere. Microprocessors, memory chips, they're types of circuits. Circuits that convert AC to DC energy and DC electricity to AC electricity. You can't connect solar panels and wind turbines to the grid without circuits. Circuits are everywhere, from robots to cars to airplanes, to your cell phones, to computers. Everything is based upon an electronic circuit. Pacemakers, various implants, artificial eyes, they're all parts of types of circuits. And our circuits curriculum starts in the second year with the Circuits 1 and Circuits 2 courses in the fall and spring semesters. The Circuits 2 course actually has a lab component which takes place in the Texas Instruments lab, Circuits lab here. Texas Instruments is a big integrated circuits company. They do anything from microprocessors to battery chargers and everything in between. They have a fab down in Portland along with offices, and they hire a bunch of our graduates, and they've supported our education program here. At the moment, the electronics lab is running in the Al Whitney lab here. Al Whitney was one of our alumni. He went to industry and then came back and taught here for many years, and the lab is named in his memory. The electronics course sequence is in the third year. 342 Electronics 1 and 342 Electronics 3, Electronics 2. And in that course, we build upon the circuits foundations. We introduce devices like transistors and dig more into the circuit design. These courses are then followed by electives in the fourth year, 444 Analog Integrated Circuit Design and 445 Digital Integrated Circuit Design. After those courses, you could go work at a company like Texas Instruments, or you could go design a microprocessor over at AMD or Intel, for example. Why don't we go into the lab? Due to COVID, we're actually running a hybrid lab, so we have some in-person students here in the lab, and then we have other students who are participating in the lab remotely. We keep our labs up to date with benchtop instruments, but the students are also using a little USB instrument that they can hook up to their computer and pretty much replicate most of their measurements at home. So we have a TA on Zoom who's working with those students, and then the rest are here. Annalise Nichols is one of our seniors as a steel over there. They're helping TAing the course, and we have several students, as I said, participating in the lab right now. They're doing their measurements. They, for the remote students especially, we mailed their parts kits. And right now they're working on transistor circuit biasing, which in next week's lab we're going to convert them into amplifier circuits.
Excellent.
Thank you.
So we're going to head now to the Kepware lab, which is just down here. One thing I wanted to point out, Nuri's probably mentioned that Texas Instrument lab. So these are endowed labs. These are labs that the companies have put in their money to renovate. They've given us money to update equipment, and they're basically supporting those labs. And one important outcome for those companies from that is that they then have access to our students. So they have an excellent rapport with our undergraduate students, and they can recruit them then for internships and co-op programs. And so the significant number, probably the vast majority of our undergrads will do usually a summer internship, one or more, with one or more different companies, and very often that internship leads to a permanent job with the company. So we're very grateful for the investment that we have from TI and from Kepware, and the ongoing relationship that leads to with the students. and the impact that has on the quality of the student experience. So let's move down then to the Kepware lab. Thank you, Neri. So Kepware is a company started by an alum. It's based in Portland, Maine, and works largely on computer solutions and programming. And so here we have a range of faculty again. You'll notice Professor Eason over here. He's multitasking. He doesn't only do balloons, he does robots as well.
Yeah.
He's going to demonstrate some of the work that we do, and this is Professor Yifang Zhu. He's really our lead, one of our leads in the computer engineering side of things. So he's going to talk a little bit about the coursework, and particularly how that relates to the lab, hands-on lab that we have, as you can see here, this beautifully renovated space. So,
as David has introduced, this is the Kepware lab, and Kepware is a software company. It started by one of our alumni. It's located in South Maine, and we always maintain strong connections with our alumni. So we build career paths, and for our future, for students, for our graduate. And Kepware, they offer scholarship, they offer summer intern, they also hire a lot of our graduate students. And here, the Kepware lab mostly are used for computer engineering and courses, for undergraduate computer engineering course. And what's computer engineering? Computer engineering mostly is program computer design and program computer or computer-based systems. So it's not just computer itself, it's all about computer-based. So in the computer-based system, pretty much is everywhere. And here just show you an example. This is a self-driving car, and with all the sensors, cameras, and try to follow the racing track. And it has motors to control the front wheel, back wheel, have sensors to detect the speed. And we teach our kids how to program this car to program and also design the car. And here I'm going to show you another example, which is Sarah. She's taking one of our computer engineering course I'm teaching this semester, computer architecture and organization. Here's Sarah.
So in this project, we're creating a 5-stage pipeline processor, and we're using both the FGA board and also a program called Quartus. And in Quartus, we both use this BDS file type system, and we also use something along the lines of Verilog, which is a type of coding language. And through all of this, we connect it up to the FGA board and connect it to a display, and we can see in real time the PC history, and this is our processor, our computer.
I think this project shows the depth of our computer engineering education. So at the end of each semester, students feel very proud that they just designed their own CPU, and it's very helpful which will help them understand or build better, faster, more energy efficient processor in the future. In additionally, they understand how CPU work, they can write much better software and applications. And another example I'm going to show you here is Professor Rick Eason, and he's using robotics in his class.
Yeah, so I teach, in addition to ballooning, I teach both undergraduate and advanced robotics, graduate level class. And as in the undergraduate class, I have the students, they're writing software to move the robot around. There's a lot of math there to try to figure out what the joint angles need to be to move it to a particular position. Right now it's playing this is a student, one of the labs, the students have to write software to play the Tower of Hanoi puzzle. Objects to move the blocks from one stack to another, never moving a big block on top of a small block and only moving one at a time. So this is actually the first time this student's program is being run on the robot. Actually, when COVID hit, I wrote a little simulator that the students wrote the code on, and today I came in the lab and just tried the code out for real on the real robot, and it seems to work good. So, like I said, it was just written with the simulator here, last semester when they couldn't be in lab. So, same software.
what would you say are the societal implications of this kind of technology?
Oh, robotics, of course, are used everywhere, especially in this kind of robot. It would be used in industry, been used for years to save Well, for one thing, it's not just not having to hire people. I mean, we like to hire people, but it's robots can work faster. They can work more precisely. They don't take breaks, and so there's a lot of benefit there.
Working environments where humans
Working environments, hazardous environments, and yeah. So it's better to put people doing some other things that aren't so, repetitive, especially repetitive things that people get bored out of their mind, and carpal tunnel syndrome, which can happen when you're doing repetitive tasks.
lifting heavy weights.
Heavy weights, yep. Yeah.
Fantastic. Excellent. Well, thank you all.
Yeah.
We'll move on to the next stop.
All right.
Please follow me. So our program is very fortunate that we embark on the engineering, science and research building. So we're moving into a component of the building now that's probably 10 or so years old, mostly funded by the state of Maine through bonds. And it's a wonderful high-end facility that focuses largely on sensors and a lot on interfacial characterization and manipulation to give sensing capabilities. So we'll see a couple of labs that are doing relevant technology. So some of the ECE labs are run in facilities here in the ESRB building, and some of our faculty have their research laboratories in here as well. So as you can see, it's a beautiful space and it's incredibly well equipped. As I mentioned about our undergrad labs, we're very fortunate to have really high-end equipment and to do some really cool stuff, which is what you'll see on the next stop. Get us in here. There we go. All right, come on in and you'll recognize Joseph again. We've got a couple of different projects. This one's quite different, but somewhat related to the initial one that we talked about.
Yep, sure. So welcome to the WiseNet lab. That's short for the Wireless Sensor Networks Laboratory. This lab is run by Dr. Ali Abedi, who's one of our professors here in the ECU department. And recently we've done some very cool projects. So this project here is actually a wireless leak detection system. And this was actually certified for flight and launched to the International Space Station in 2016 on a Japanese Space Agency rocket. And this payload was operated by astronauts aboard the ISS, and it collected data for months and actually was returned to us on a SpaceX rocket, and we were able to downlink the data from it. This is the first ISS payload made at the University of Maine, and so this payload actually detects leaks on the International Space Station by using ultrasonic acoustic noise detection, and it employs a original algorithm written in our lab to exactly pinpoint leaks on the ISS. And as you might know, that's actually leaks on the ISS has actually been a problem in the past couple of months. So this is a very important piece of technology. And another space mission that we've actually been working on is a CubeSat. So this is actually a 3D printed representation of the structure of the MESAT-1, which is the first CubeSat from Maine. Just a few months ago, we got our proposal accepted by NASA to build and launch a CubeSat into orbit in 2023. And for that project, we've actually been working with local high schools in Maine. They conceived the science mission, and once we get this into orbit, we'll get that data back to them, and they can do science with real data collected from a space mission. So yeah, we have quite a few space missions going on here. So it's University of Maine and the ECE department is a pretty cool place to come, especially if you are interested in space. And actually two students who worked on this project, one of them works at NASA now at Goddard, and one of them works at SpaceX. So if you think that's cool, then come work in the WiseNet lab for Dr. Abedi.
So just one point to make there, and it's a really good one that Joseph's brought out, is those research opportunities, they're not specific just to this lab. Every lab that you see here in the EC department have undergraduate students in them. Many of them have graduate students in them. They have large funding portfolios, whether it's from NASA, whether it's from the Department of Energy, Department of Defense, all kinds, NSF, all kinds of different agencies funding them. Even NIH with some of the biomedical applications. So there's massive opportunities for students, not just to be in the lab and in the classroom learning, but actually getting out and applying that knowledge to be developing new technologies. So when I started this tour, I talked about having a career that was impactful, waking up in the morning and wanting to go to work. That's the kind of job that you want. You don't want just to receive a good paycheck, that's one thing. You want to be changing the world, and this is how you begin doing that. So let's move on. Thanks so much, Joseph, as ever, much appreciated. We've got just a couple more stops. Okay, here's another familiar face. Mauricio Pierre again. He's going to talk to you about his high temperature sensing work.
Just be careful with this door there, right, so that doesn't get you on the back. So this is the microwave acoustic laboratory. It's a research laboratory for both undergraduate and graduate students, right? So undergrads and grads work together here to develop research. It is, again, a multidisciplinary laboratory. It involves electrical, mechanical, chemical engineering, biomedical engineering, and physicists as well. And it is a high-tech, world-class type of research. We do laboratories, we do wireless sensors and wireless devices for applications that include biosensors, so for instance, detection of E. coli, biomedical device, detection of pancreatic cancer. We developed sensors for NASA, for inflatable structures, right, both habitats in the moon and sensors for antennas, right, in Mars, that type of inflatable stuff. And also harsh environment, high temperature, harsh environment sensors, as David mentioned. That's the most recent type of research that we have been doing. Most recent, but we have been developing this for almost 2 decades. So it evolved from research to technology that transitioned into commercial applications, right? So we were very proud to be the very first place to install sensors in turbine engines rotating at temperatures up to 700 degrees Celsius at 172,000 Gs, right? G is the acceleration of gravity, is what keeps us standing here on Earth. So imagine 170,000, that stuff, and the sensor stayed put there, and we could interrogate temperature, right? So this, for instance, are some of the structures, right, that we use to develop. This is a 747 blade. The sensor itself, it's placed there just to show, right, in the blade. This is a rotor, right? Actually, this is a jet cap that we used for test here. And I could talk for 40 minutes, we don't have that time. But this is a turbine engine that we use for test. And then from this type of turbine engines that we use for test, we went for tests in major turbines from the major turbine suppliers that you can think of, right? So the devices themselves are shown here, right? So these are the device in wafer. We cut these devices, right? And then each single device is the one that we can see on the blade there, right? So for instance, here we have one wafer with probably 80 or 100 of those devices. So Anin, who's in there, was a student here. I'll let him talk a little bit about his work, right? He did his undergrad here, his grad here, and now he works in a related area. So, Anin.
Hi, my name is Anin Maske, and I'm originally from Nepal, and I came here to do my undergrad. After finishing my undergrad, I looked at the research potential that the university had, or department had, and decided to stay for grad school. And I worked in this very lab for several years, working on my doctorate degree in exactly this area, harsh environment wireless sensors, which has immense potential. And all of the work that I did, now I'm transitioning it to the industry, where the work is actually being done at a company, a Maine-based company that was spun off from the university. And I'm currently the lead engineer there, and we're making this into reality, which is pretty amazing.
So, Anin, I mentioned here the aerospace Department of Defense application, but there's a recent one is actually the energy sector, and Ani is working on that, so are my other students and co-workers here that I'm going to mention. But it's interesting, for instance, to relate this to reality, that work that we are doing in terms of these harsh environment sensors can actually monitor temperatures right up to 1,000 degrees Celsius. And 1% increase of efficiency in these power plants result in hundreds of millions of dollars of saving just in the United States and power plants, right? Coal power plants, actually. But it's applicable to other power plants. Not to mention that it also has a huge impact in the environment because it decreases the pollution due to the better efficiency in fuel burning, and saving costs as well, and increase safety, right? Because you can use the sensors for preventive maintenance, which means if something starts to go wrong, by monitoring them at harsh environment, high temperature, you know that you have to do preventive maintenance. So Luke is working on, he's a research associate here, he's working on development of some of these parts. Well, not going to take your thunder.
Yep. Hi, my name is Luke Dusat, and I'm a research scientist here at the university, where I help several of the faculty members in the Department of Electrical Engineering with their research. And specifically, one of the projects that I'm working on right now has to do with developing advanced coding and coding materials that we're applying onto some of the sensors that we're developing here and the other associated sensor components, so that they could be protected and have longer lifetimes when they're deployed in some of the harsh environments and high temperature environments that they're designed to work in. And as a matter of fact, I have an ongoing experiment right now where I'm actually testing some of these sensing components that would better illustrate what type of tests we do here and what it looks like. So as I mentioned, a lot of the sensors that we develop here for the current projects that we're working on are intended to be deployed in very harsh environments, very high temperature environments, such as in power plants, on turbine engines, things of that nature. So right now I have a sensing device that's inside this furnace. Now this furnace is one of several furnaces that we have here in the lab that we use to simulate some of these harsh environments. So this furnace right now is operating at 800 degrees Celsius, which is approximately 1500 degrees Fahrenheit. So it's very hot, okay? And I have a device in there right now that I'm heating up at this temperature, and I'm monitoring its electrical response over time and temperature to measure how it's degrading over time. And this is going to help to inform us what type of coatings we could utilize to help increase the lifetime and increase the performance efficiency of these sensors. So what I'd like to do is show you what it actually looks like inside one of these hot zone environments. Now, this is something that you normally would not want to advise somebody who doesn't know what they're doing to do, because it's very hot in here, so kids, do not do this at home. But I'm going to crack open this door and you're going to see what it looks like inside one of these harsh environments. Now at 800 degrees Celsius, materials start to glow. That's how hot they get. And on that device I have several little wires that I'm actually testing their performance as a function of this very high temperature environment. Now, one of the great things about working here at the university and being a student within the Department of Electrical Engineering is that there are many different research projects going on which provide students a lot of opportunities to be a part of these research projects, to actually get hands-on experience conducting some of this cutting-edge research and learning how to use some of these cutting-edge research tools that we use, giving you hands-on experience and knowledge on how to do this. And a lot of these skills are directly transferable to help you get jobs once you graduate. So a lot of exciting research is being done here and a lot of great opportunities for students to be a part of.
Talking about tools, right, that's David, he's a graduate student here. He's doing tests on a table that weighs about 2,000 pounds, and the reason for that is so that it filters vibration of the building, right? So even with the hammering of the new building on our back here, that table does not oscillate, otherwise it would destroy, because the tips are the thickness of a hair, right? And David is testing there a resonator device that we can see there. That's frequency, right? So it's very selective in frequency. I'll let David describe his work.
Yeah, so this is a high temperature resonator that we use for sensing in harsh environment applications that were discussed just a bit earlier. And yeah, so this is the sensor response as as a function of frequency. And yeah, so basically just looking at this response, we can determine temperature and strain or a bunch of other types of...
On the camera, is it?
Yeah, and then and this is a picture of device on the camera.
That's the actual device that's being tested, right, in that machine that I mentioned there. And so that you guys have an idea, right, the distance between the center to center here, this place to the space is 1 millimeter. And all this thing here is our fingers, right, of about 4 micrometers, which is a hair divided by 15 or 20 diameter of a hair. So those are the dimensions that we have to deal with. And this thing is fabricated on downstairs, right, on a clean room that you guys are going to see while we walk downstairs to another lab.
Okay. Ready to move on?
Yep.
All right, well, thank you all. Appreciate your time. All right, so now we're going to walk past the clean room, which is a part of the ESRB building. Yuri knows a little more about this than I do, so he's going to give us a bit of a tour of that.
So previously, while talking about circuits, I mentioned microprocessors, memory chips, and Professor Mauricio talked about his research on the high temperature sensors. A clean room is where these types of devices are manufactured, and we have a class 100, class 1000 clean room, which is for an academic institution unique in this state. Our students are able to actually go in the clean room and work there as parts of research experiences, or they can also take the microelectronic processing course, EC464, which is a technical elective. And we have a teaching clean room, and they also spend some of that course in the actual big research clean room as well. You can think of the clean room, it has to be so-called clean. There have to be very few dust particles because the devices that we're talking about are on the order of micrometers in size. So you're talking about something that is about 1/50th of the diameter of your hair. This is the clean room, and it's set up in different bays. We have furnaces in there which bring up wafers to high temperatures, chemical etching processing parts, as well as dry processing areas. You can think of a manufacturing of an integrated circuit in a sensor device, for example, like Mauricio's, as you add materials to the wafer, and then you remove materials on a sequential step. In a modern integrated circuit, like a microprocessor, you're talking about dimensions. The smallest device dimensions are 6 nanometers. The smallest we can do in this clean room is 1 micrometer, so about 1/50th of the diameter of a hair, human hair.
Very close to the dimension of those devices that I showed
Yeah.
upstairs.
Yes. So to go in there, you have to gown up. It's almost like a spacesuit to get in there. This area is all yellow light out here because this area is used for photolithography, where the patterning on the surface of the wafer takes place.
And if it's not yellow, the UV light
Yes.
would actually destroy the fabrication process, right?
Yes. So that's why there's yellow filters there. Can I mention this?
Sure. While we walk here on our left hand is some of the equipment that use very high vacuum to fabricate those devices that I was mentioning upstairs that withstand temperatures up to 1,000. And Morton is one of our PhD students working with a colleague in the Department of Physics. And he is actually researching some of these films that we are talking about that I showed in the device upstairs.
It's known as the BSM 2000, I believe.
The big shiny machine, yes.
Got a chance to get on this?
Not every day someone hands you a jet.
Have you seen the movie that the guy flies with this? I show the kids, right?
So we're moving on to the opposite wing at Barrows.
It's from Switzerland.
Our next stop is the anechoic chamber. Anechoic means it doesn't make any echo. In this case, it's not an acoustic anechoic chamber, but a radio frequency wireless anechoic chamber. It's where we do antenna testing. Why do we do antenna research? Part of our research area has to deal with wireless, whether it's in communications or applications like radar. You cannot have wireless without antennas. That's what transmits the signal, right? Whether it's your radio antenna in a car, the little Wi-Fi antenna. In your cell phone, you probably have at least 6 antennas because you have multiple, you have cellular, Wi-Fi, Bluetooth, and various other technologies that need different antennas at different frequencies. And antennas will transmit their signals in different ways. Your car antenna is a so-called omnidirectional antenna. It's meant to receive a signal from every direction. Whereas, if you think about it, a radar's antenna is supposed to focus that energy, electromagnetic energy, like a beam, like a flashlight focuses a beam. So the instrument that's in this box helps us test what an antenna does. Is it working properly? Put down here. Watch your step. Essentially, we put an antenna that we're testing in there. You don't want to get too close in there because this is an anechoic chamber. It's a metal box, and essentially, if you go in there, your communication will get cut. It will kill Wi-Fi.
The beauty of this box is that as if you were in space, right? No signal enters the box, and essentially all the signal is attenuated by these spike cones that you see there. So
Yep, they absorb the radiation, the electromagnetic radiation. So whether you're dealing with cell phones or Wi-Fi, if you're testing anything in here, they will kill the signal. And then we essentially put the antenna in there. You can, I guess, take a look if you want from the door. Just don't go in there because you'll lose your connectivity. And then essentially we connect the systems to this instrument here. And then the antenna rotates, and on the other end, there's a probe antenna which goes up and down and rotates. And you see a pattern like this, which tells us that the antenna that we had tested at that time, not the one that's in there right now, actually was directing all of its energy in one direction, and it wasn't radiating in other directions, and that's what you want, but what the person who had that antenna wanted. We use this for research, but we also use it for teaching. Mauricio's microwave systems course, students actually make their own antennas and they come and test them in this equipment. We have several companies actually that are down in southern Maine that do antenna design. They're out in the gray area. One of them is Dielectric. I forget if they've changed their name back to Dielectric again or not, but there have been a number of companies there are a number of companies that work and hire our graduates.
Excellent. Thank you, Neri. Okay, so at this point I think we'll wrap up. Some of the highlights I think I'd like to touch on. It's a comparatively small program. Our incoming class is around 60 to 70 students per year, pretty equally split between electrical and computer engineering. We have a number of dedicated faculty. They really care about their students. They go to great lengths to integrate what they're learning in the classroom with what they can learn in the lab and further supplement that with research. So you saw many of the students here today talk about their research experiences. And what they're doing, of course, is putting what they're learning in courses into practice in the labs. And then they're doing internships, taking that knowledge out to local companies. The companies are seeing that value, and then they're trying to recruit those students into full-time jobs. So it's a wonderful system that works incredibly well. It's a very tightly integrated program that we're very proud of. So with that, I'll pass it back to Dana.
Thank you very much, Dave and Mauricio and Nuri and the rest of the tour guides. I think you got a great tour of our electrical and computer engineering program, and you can see what this has to offer. And remember, for the College of Engineering as a whole, we have 11 different engineering and engineering technology majors. The world is demanding more engineers, so the fact that you're considering a career in engineering is outstanding. I said earlier that we have a 99% placement rate for our graduates. I was actually shading that down a little bit. The last survey we did, and we do this survey 6 months after graduation, actually 100% of the students said they're either employed full-time or in grad school full-time. And that's just a tremendous record, and it's due to the quality of the education you're going to get at the University of Maine, a very hands-on education. Would love to see you here as students next fall. If you have any questions, again, my name's Dana. Just reach out to me through the College of Engineering. Thank you so much for joining us for today's tour.